everybody, it's Dr. Blanchard. Originally I was supposed to be going into lab and filming some of these videos for you to watch, but unfortunately I've been sick, so I don't really want to go to campus. You might hear me cough throughout these videos. But in any case, I can introduce my co-host. This is Scout. Here's Scout, look at the camera. Look at the camera, look. He's a 3-year-old Australian Labradoodle, and yeah, so there's probably going to be doorbells and people talking in the middle of these videos, but I'm going to do my best to film something from home. So my goal is to go ahead and show you, give you an overview of the Experiment 7 lab, Solutions and Dilutions, which is actually, luckily, an ideal lab to be doing from a kitchen because I'm making saltwater solutions. So I'm going to first give you an overview of the lab, just with some glassware images. Then I'll actually demonstrate the lab to the best of my ability. I think this is actually going to work pretty well. And then I'll go through some calculation steps with you. So to begin with, I just want to show you some images of the glassware that you would have used if you were in the lab and the steps you would have gone through to make your saltwater solutions. So we would have started with this between 43 and 45 grams of salt. And so here, I'm giving you the mass of this salt. 43.908 grams of sodium chloride is what we're starting with. And it's actually quite a bit of salt. You can see I'm holding it in a dish. So it's kind of like a handful of salt when you're talking about 43 to 45 grams. And then you would have transferred that salt into a volumetric flask, a 250.00 ml volumetric flask. Remember, a volumetric flask is a very accurate and precise piece of glassware. And what you would have done is you would have, there's a calibration line here that's really hard to see. I'm going to trace over it in black. So you would have put your salt into the flask, and then you would have just started filling the flask up with water. So if I color this in with blue, maybe you can tell that I'm filling it with water. And you would have filled it all the way up to this calibration line. And just like anything we've done in chemistry before with glassware, we would have filled it until our meniscus sat right on that calibration line. So then if the meniscus is sitting right on the line, we have exactly 250.00 mLs of water in that flask. So after we made our saltwater solution, we would have just transferred our water into a beaker. The beaker here is just a holding tank. We're just doing it because it helps mix up the solution a little bit better, and it's a lot easier for us to pipette out of a beaker than out of a volumetric flask. So we would have poured the whole solution into this beaker. Just pretend that this was like a 400 ml beaker, so that this here would be all 250.00 mLs of our salt solution. So after we poured our solution into our beaker, we would have used, I'm sure, your favorite piece of laboratory equipment, a volumetric pipette, to transfer our solution to different volumetric flasks. So what we're doing is, first we have this solution here, and this is called our stock solution. And the concentration of salt is high, so high salt concentration. And what we want to do is we want to dilute it. We want to make some lower concentration salt solutions. And this is a pretty relevant type of lab for anybody who's going into any type of research down the road, especially if you're doing anything with medicine, because what happens is you want, when you're dealing with medications or biological systems, you're generally talking about making very, very dilute solutions or very low concentration solutions, and you usually cannot make them directly. Like your instructions, if you wanted to make a solution, might say to put 0.0039 grams of an enzyme into solution. And
you can't really do that because your balance can't weigh 0.0039 grams. So what you would do is you'd make a really concentrated solution first, and then you dilute it down to something that was much lower concentration. So in this case, what we would do is we would have 3 new volumetric flasks for our diluted solution. We would have had a 500 ml volumetric flask. We would have had a 250 ml volumetric flask, and then we would have had a 200 ml volumetric flask. This image is actually a 100 ml volumetric flask. So a 200 ml would be pretty close in size to the 250, but this is the best I could do for images. So your instructions would have said to transfer. So you're going to transfer this solution. So you're going to put these volumetric pipettes. You would, use them to get some of your stock solution, and then you would transfer to your other volumetric flasks. So the instructions would have said to put 50 mLs of your stock solution into your 500 ml volumetric flask, put 50 mLs of your stock solution into your 250 ml volumetric flask, and put 100 mLs of your stock solution into your 200 ml volumetric flask. So what would that look like? Well, if you put 50 in our 500, maybe it would look about like this. So here's our stock solution, and let's make our stock solution, we'll make it green. So here's our stock solution at the bottom of our 500 ml volumetric flask. And then we needed to put 50 in the 250, so that would be about a fifth, so maybe it fills up to here. So here's our stock solution in the bottom of our flask. And then finally, we would have put 100 in our 200 ml volumetric flask, so it would look like that. So then all you would need to do is dilute it with water. So you can see if you fill this up the rest of the way with water, in this first solution, first diluted solution, it's mostly water and then, some of our stock solution. In our second dilution, you can see, well, relative to the amount of water, there's more of our stock solution relative to the amount of water than there was in our first dilution. And finally, in our last diluted solution, here, this one has half of the final solution is our stock solution, and half of the final solution is water. So when we actually mix these up, this one is least concentrated, and this one over here will be our most concentrated salt solution. So these are, relative to our initial solution. So here's our stock solution. This is obviously our most concentrated salt solution. But once we finish the dilutions, these are all less concentrated than our original solution, but going from, most to least concentrated, this first solution right here, this is our most concentrated solution. This one is the one in the middle here, this is a little less concentrated, and this one is the lowest concentrated solution. So once we make our solutions, then what we would want to measure is the density of our solutions, because the density, remember, D equals M over V. Let's fix that. D equals M over V. So as the mass of salt in each of the solutions changes, the density changes. So because the one in the most concentrated solution is going to have the highest density because it has the most salt. The least concentrated solution, this has the lowest density because it has the least salt. We wouldn't have measured the density of our stock solution. Again, this is our stock solution right here. We wouldn't have measured the density of that. We would have only measured the density of our 3 diluted solutions, plus we would have measured the density of a flask that was just pure water. So we would have had one flask that was just pure water. because we wanted to know the density of that also. So how will we get the density? Well, we could have done what we did in lab 1, which was, we could have gotten the mass on a balance, and then we would have already had a measurement for the volume. So we could have done that, but instead what we would have done is use something called a hydrometer. So a hydrometer is something that is designed just to measure the specific gravity of water, which can easily be converted to density. This is an image of a hydrometer right here. And so this one right here, this is the image of the hydrometer. And we would have put that into our solutions and it would have floated. So on the left, this image here, which is hydrometer and beer, hydrometers are used in the beer brewing industry to determine the density of beer, because the density of beer lets the brewers know what the sugar content is. So it lets them know when the brewing process is done. Hydrometers are also also used to measure the density of salt water in fish tanks. So if you happen to have or know somebody who has a saltwater fish tank, you need to have a very specific concentration of salt for your fish to survive. So the hydrometers that we actually buy for lab, these guys, we actually get them from a pet supply store. So if you walk into any pet supply store, these are easily available. So once we would have measured the specific gravity, which is what the hydrometers measure, we could easily just convert it to density with a calculation that I'll help you with. So that's an overview of the glassware, and then I'm going to actually show you now how to, like what this lab would have looked like.
So here's my setup for this experiment. What I have is my salt on a balance, and I have a saltwater solution that I've already prepared. And the reason why it's blue is because I added some food coloring to it, and I did that to give you a visual so that you can see what happens as a solution becomes diluted. And then I have my 3 other containers where I'm going to make my diluted solution. And then finally I have the water that I need to make a dilution. So as I've said, I've already actually put this salt into my stock solution. So we already have salt dissolved in there. But this is what I use to show you approximately what 45 grams look like. So I have my kitchen scale. And the data that I'll be providing you with is actually data that luckily I already had. I'd already taken measurements for this lab, so I'll be giving you very precise numbers. Obviously, I can't read this to 3 decimal places, but the data I will give you has actually been measured in lab. So the original stock solution, this was filled originally up to 250 ml. So what you can see is I've removed 50 mLs of it, and I put it into this secondary container. And now I'm going to add water to dilute that to 500 mils. That's the first dilution we're supposed to be doing. It's a 10-fold dilution going from 50 mLs to 500 mLs. So there we have it. So there's the first dilution. So I transferred the contents of the first dilution into this glass here, just as a holding container. And now I'm going to make the second dilution. So again, we started to put 50 mLs and dilute it down. So we started with 200 mLs. I removed 50 mLs already, so this is down to 150 mLs. I've transferred it into this flask again. And so this time, I need to dilute to a total volume of 250 mLs. So there is our second dilution. And then again, just so you can see the procedure, then I transfer this into our holding glass, just because I don't have too many of these. So here is dilution 1, and right next to it is dilution 2. It's dilution 3, so again, I transfer this time 100 mLs of our stock solution. I put it in here, so here this one has 100 mLs in it. And this third dilution, you're supposed to dilute to 200 mLs for a total volume. So there we go. We went from 100 mLs to 200 mLs. And again, I'll just transfer it to a secondary container so that we can compare everything. So here are our 3 diluted solutions. Dilution 1, dilution 2, and dilution 3. Dilution 3 was our lowest total volume solution. We only had 200 mLs total volume. So what I did so that we can compare the colors better is I removed some liquid from these 2 glasses because I wanted the 3 glasses to be at about the same height, just so that the liquid would look the same in the 3 glasses. So our first dilution is our 1 to 10 dilution, meaning we put 50 mLs of our stock solution in our flask and diluted it to a total volume of 500 mLs. Our second dilution is our 1 to 5 dilution, meaning we put 50 mLs of our stock solution into our volumetric flask and diluted it to a total volume of 250 mLs. And our third dilution is our 1 to 2 dilution, meaning we put 100 mLs in our volumetric flask and diluted it to a total volume of 200 mLs. So as we said earlier when I was giving you the overview of the lab, this is our least concentrated solution, and this is our most concentrated diluted solution. Remember, we did start with a stock solution. I'm going to put it here. Unfortunately, I don't have very much left. So I don't think you're going to be able to tell the color difference between the stock solution and our third dilution. But this is our most concentrated solution. So what we did is we took the stock solution and we put a little bit of it in each of these 3 dilutions to dilute it down, to lower the concentration. So if you look at our 3 diluted solutions, though, if you compare the color, you can clearly see that dilution 3 is our most concentrated solution. It's darkest in color. Solution 2 is our solution right in the middle. It has a medium color. And dilution 3, our least concentrated solution, clearly has the palest blue color. So just once again, the reason that I added the food coloring dye was to give you a visual of what is happening to density. You are not here to measure density. So the color is there to just kind of show you that this solution is going to be our most dense solution. This is dilution 3. It contains the most salt, so it has the highest density. Density is going down, and then we have dilution 1. This is our least concentrated solution. It contains the least amount of salt, so therefore it has the lowest density. I needed a mental break from the video making, so here I'm showing you my chickens. They're the hens. Kind of happy I have them right now so I can always get eggs in this quarantine type of situation. Here's the rooster. He's pretty mean. Can you see those spurs on the back of his legs right there? So if we let him out sometimes in the yard because they like to get out. But if you are out there and the rooster sees you, he'll come charging at you, and then he'll fly at you with those spurs. He'll lift his legs up and try to attack you with those things. They're pretty nasty, so we're pretty scared of the rooster.
All right, so I'm back inside, ready to tackle some of these calculations. And so just as a recap, what we did is, in our home lab here, we added salt to water, added some food coloring, and we made a stock solution. The stock solution, and you're going to need this data, the stock solution had a mass of sodium chloride of 43.908 grams, and the flask volume for the data that I'm going to give you was exactly 250.00 milliliters. Now I know right here that this is approximately 250.00 mils, but the data that I have that I'll give you the densities for was made in a 250.00 ml volumetric flask. And your directions in your calculations, or in your procedure actually, said to record the flask volume in liters. So when you move from milliliters to liters, You're dividing by 1,000, which means you're moving your decimal place 3 places to the left. So that would mean my flask volume is now 0.25000 liters. Can't lose any zeros. So what's important to note is that I have 5 sig figs right here in my mass, and I have 5 sig figs in my volume. So please go ahead and record the mass of sodium chloride and your flask volume someplace, whether it's going to be in your lab notebook or if you're going to do everything in Notability, just record that someplace. And then, just as a reminder, what we did is we took our stock solution and we used it to make 3 diluted solutions. Okay, so dilution 10 was a 1 to 10 dilution. Dilution 2 was a 1 to 5 dilution, and dilution 3 was a 1 to 2 dilution, meaning that this is least concentrated in terms of salt, and this would be most concentrated in terms of salt. And you can kind of see that because you can see the color darkening from least to most concentrated. And likewise, this means this is going to have this solution, dilution 1, will be the least dense, and solution 3 will be the most dense. So what you need to know, so what we want to do is we have our stock solution, we need to calculate the concentration of the stock solution. And then we're going to need to calculate the concentrations of salt in our 3 diluted solutions. So the first thing we should do is calculate the concentration of salt in the stock solution. So concentration, which is measured in molarity, so I'm going to say M for molarity, equals moles solute per liter of solution. So moles of solute, we don't know how many moles of solute right now we have grams of solute. So we have 43.908 grams of NaCl. And you need to convert that into moles using the molar mass. And I'm not going to show you how to do that because I think you know how to do that. So what I'm going to tell you is that use a molar mass of NaCl of 58 point, I think it's 443 grams per mole, and use that to find how many moles of NaCl you have. So I'll say X. So you're going to figure out how many moles of sodium chloride you have. So you're going to solve for X. And the reason why I want you to use a molar mass with 5 sig figs is because of what we set up here. Mass of sodium chloride has 5 sig figs. The flask volume has 5 sig figs. So therefore, you don't want to limit the number of sig figs in your total molarity calculation by using too few sig figs in your molar mass. So we want to make sure we have 5 sig figs in molar mass. So when you calculate moles here, you need to make sure your answer should have 5 sig figs. So I did just confirm with myself that the molar mass of sodium chloride is indeed 58.443 grams per mole. So you're going to calculate moles of sodium chloride, which you're going to have with 5 sig figs. And after you get that, molarity of the stock solution is going to be your moles, X moles, NaCl, divided by 0.25000 liters. And so molarity, your answer here should have 5 sig figs. And if you did the calculation correctly, it's going to be approximately 3 molar. So it's going to be 3 point something molar, 3 with 4 more decimal places so that you get 5 sig figs. Looking back now at the calculations, you'll see what we just did was we did step 1.1, which says convert mass to moles. and we did you should have done on your own step 1.2, which is calculate the molarity of your sodium chloride stock solution. So now we're going to move on to step 1.3 to calculate the concentrations of the 3 diluted solutions. So what we know is that going into each flask for the dilution, we were putting in approximately a 3 molar stock solution. For dilution 1, we were diluting it 1 to 10 because we put 50 mLs in the flask and then diluted it to 500 mLs. So if we take a molar solution and we dilute it by a factor of 10, this is going to be about 0.3 molar. It's just 3 divided by 10. Solution 2, we're taking a 3 molar solution. We're using 50 mLs of it. We're going into a 250 mL flask. So that's a 1 to 5 dilution. So if we take 3 molar, we divide it by 5, we know this is going to be about 0.6 molar. And a 1 to 2 dilution, we put 100 mLs in a 200 mL flask. So you're just cutting the concentration in half. So this is going to be approximately 1.5 molar. So your answer is going to be about that. So that's your guideline. And in order to do the calculation, let's see, the calculation is this. It's initial molarity times initial volume equals final molarity times final volume. Your goal is to find the final molarity. You know everything else. So the initial molarity in all of your calculations, it's always the 3 molar solution. Remember, 5 sig figs here. Your initial volume is the volume that you pipetted, the volume you used to make the dilution. So for dilution 1, we used 50.00 milliliters of the stock solution. For dilution 2, we used 50.00 milliliters of the stock solution. And for dilution 3, we used 100.00 milliliters of the stock solution. So those are the initial volumes. And then what did we do? We diluted it down to a final volume of 500.00 milliliters for dilution 1, 250.00 milliliters for dilution 2, and 200.00 milliliters for dilution 3. So these are our final volumes, and these are our initial volumes. And what's important to note is that in some cases, we have 4 sig figs in our in our initial volumes, and in this case, we have 5 sig figs. So your final molarity that you're going to calculate will either have 4 sig figs for dilution 1 and 2, or 5 sig figs for dilution 3, because we want to keep track of our sig figs in all of our calculation. So let's just take a look at the simplest case, which is for dilution 3. If we were going to do this, we have approximately our 3 molar solution, and our initial volume, we have 100.00 milliliters of it, equals the final molarity that we're trying to solve for times our final volume, 200.00 milliliters. And this is what I mean when we're talking about the 1 to 2 dilution. Take a look at what happens. So we have approximately 3 molar times 100.00 milliliters, and then I'm just going to move over the 200. That equals our final molarity. You see, here is 1 to 2. So we're just taking a 3 molar solution, the 3 molar concentration, and we're dividing it by 2. So that's how I know that I should get approximately a 1.5 molar concentration for my for dilution 3. So you're going to do these calculations, and then you're going to fill in concentration right here with the proper number of sig figs. So again, it's 4 sig figs, 4 sig figs, and 5 sig figs. So let's take a look at where we are in our calculation. So we just did calculation 1.3, and now we want to move on to calculation 1.4, which is calculating the densities of your 3 diluted solutions. So for this, I have to give you specific gravities. So through the magic of technology, I just moved the data table around a little bit. I added some headers. So you're going to need to have this type of data recorded. And so what I've given you in the last row are specific gravities. So these are the specific gravities I measured in the lab for these 3 diluted solutions and also for pure water. So as far as pure water goes, we don't have to make a pure water solution, so we don't have an initial volume or a final volume. Concentration, what is the concentration of salt in pure water? The question is, how much salt is in pure water? And the answer to that is 0. So therefore, the concentration here is going to be 0 molar. So you're going to have, even though these are approximately 0.3, 0.6, and 1.5 molar solutions, you're going to have your exact molarities calculated with the proper number of sig figs. And then what we can do is we can calculate density. So density, which has units, we're going to give it units of grams per milliliter, we calculate using specific gravity. So note that specific gravity doesn't have units. In order to calculate density, density is equal to specific gravity multiplied by the density of pure water, which changes with temperature. We would like you to use 0.99777 grams per milliliter. So to get densities, these values here, all you need to do is multiply these specific gravities times the density of pure water. Again, sig figs, 1, 2, 3, 4, 5 sig figs, and this has 5 sig figs. So the 4 densities that you calculate should also have 5 sig figs. And as for the units for density, well, when you multiply specific gravity of your 3 diluted solutions and also pure water, you're going to do those all separately, multiply them by the density of pure water, which has units of grams per milliliter. Your answer will have units of grams per milliliter as well. And I know it seems odd that to find the density for this solution, which was pure water, right? I know it seems odd that you're multiplying by a specific gravity of pure water, but you are doing it correctly when you do it like that. Now that you've calculated density for your 3 diluted solutions and for pure water, let's take a look again at where we are in the calculations. So we just finished step 1.4, and now let's move on to step 1.5 here, which says to create a graph of density versus sodium chloride solution. So what's going to happen is you're going to create a graph, and the graph is going to look something like this. So you're going to have on your x-axis will be sodium chloride concentration. On your y-axis will be density. It's important to remember to add your units when you're making a graph. And then you'll plot your 4 solutions on the graph. So you should have a data point at 0 molar, where the density is going to end up being around 1. Then you'll have a data point at 0.3 molar, at 0.6 molar, and 1.5 molar. So you can see here the data points that I've already added to the graph. And so what you should expect is that all of your data should fall in a straight line. And then you're told to add a trend line to your data. So this is very similar to the graph that you would have made for the last wet lab on limiting reactants. And when you add a trend line, you always want to get the equation. So the equation is always in the format of y equals mx plus b. And you do need to know what y is and what x is. So in this case, our y-axis is density. So density equals m. That's going to be a number. You're going to have a value for this that will be determined when you fit the trend line. So y equals m for the slope times NaCl concentration, those square brackets mean concentration, plus b. The b is you're going to have a value for this. This is your intercept. And again, m is your slope. So you'll have values here. And you'll also get an r squared value. And r squared can go from 0 to 1. 1 indicates that all of your points lie perfectly on the straight line, which you can see here, mine aren't perfectly on a straight line, but they're really close. And yours should be really close too. So that would mean you're going to get an r squared valued probably in the range of 0.98 to 1.0, somewhere up there, because this data should fall on a straight line. And what we want you to do with this equation is to go ahead and go ahead and predict a sodium chloride concentration given an unknown density. So the unknown density I want you to use is actually, I'm giving you the unknown specific gravity. So I'm saying if the specific gravity of the solution is 1.038, convert that to density, just like you did before, by multiplying by the density of the pure water. So figure this out. You're going to get a value for that. And then, and I shouldn't say x here, I'll say, so you're going to get a density, which is a y value. And then you're going to go ahead and you're going to use this in the equation for the line. So your value here is going to be a y. So you have your y equals m times sodium chloride concentration plus b. What is this? Solve for this. What is your unknown sodium chloride concentration? And the way that you're using the graph to do that, so you can do it visually from the graph, but the line gives you a better value, gives you an exact value. So let's just say, for example, our unknown density ends up being right here. So here's our unknown density, and if we want to know our unknown concentration, we would just figure out what the x value is given our y value. I don't really want you to do that visually. I really want you to use the equation for the line to give me an exact value for sodium chloride concentration. So now that you've finished your graph and you've predicted your concentration of the unknown solution, let's see where we are on the calculations. We've now finished all the way through step 2.1. We've used the equation for the line and the density of the unknown to find the unknown sodium chloride concentration. So the next page of your lab manual looks like this. It asks you to make a results table. I've crossed out some stuff you don't need to do. So we just need you to, to summarize the concentrations and densities of the 3 diluted solutions of pure water and of the unknown solution in a results table with a title. Please, it cannot be results. Come up with the appropriate title. As for the discussion, you really can't do the discussion as written. So to the right, I have an alternative. I just want a 3 to 5 sentence summary of the experiment, along with 3 to 5 sentences of feedback on what I've done here. It's okay to be perfectly honest. This is not a perfect situation. We're just doing the best we can. But if we ever have to do something like this again, it would be great to get a little bit of feedback just on what you liked, what you didn't like, what you'd like to see improved. And as far as the lab report goes, your lab report can be in electronic format, or it can be written in your lab notebook. That means you can write it in Notability, you can type everything up in Microsoft Word or another software package, or you can go ahead and write it in your lab notebook and you'll just submit photos. And what we need in the lab report are the experimental goal, data tables, calculations, the results table, and a discussion. And you'll upload this all as a single document to Blackboard. I did provide some videos for the previous lab on how to upload to Blackboard. So if you forget how to do it, just go ahead and take a look at that. So go ahead, finish this up. You are done, hopefully at this point. And thank you very much for your attention.
Scout, we did it. We finished the lab. Give me 10. Give me 10. Oh, good boy.